Hello YouTube viewers, welcome to my show Rocket Monday. In today's episode, we're gonna take a closer look at Starlink's satellite. So let's dive right into it. So what it is, if you have checked my last video about basically Starlink project, the whole idea is basically a global satellite internet. This is the step one of it. This was the mission insignia. Now, this will be a part of LEO constellation, basically low Earth orbit constellation. Now, the idea is that there will be multiple orbits, orbital planes, and each plane will have more than 60 satellite. Now, or 60 satellite is bare minimum. So, each plane, each time they will launch a rocket, they will take care of one orbit. They're supposed to have around 15-16 orbits to get a sparse coverage, 80 to 90 orbits if they want like a really dense coverage. And their target is like basically they launched 60 off first, and their target is 12,000 satellite. Now do understand this very thoroughly. They don't need 12,000 satellite. 12,000 satellite is their calculation based on the idea that they want to take care of whole planet and population, like of course population growth and all that. So all those considered, then they need 12,000. They can easily provide very good, very stable, thorough planet-wide coverage in less than 5,000. They can take care of it, and they know that that's why they are moving in step by step. So like step one of the constellation, they're not gonna like densely pack these orbits. They will be like spread it out, like make sure we can give coverage everywhere. First generation is just for coverage, then they will have high bandwidth, then they will have like maximum bandwidth where they can take care of the whole population. Basically whole of India can communicate through the network and it won't slow it down. Whole America can do that without slowing it down. Whole of Australia, whole of Africa. That's why they need 12,000. And this also gives them basically like where they will get the license for 12,000 right away, and if they are making profit, they will keep updating. If they are not making profit, they don't have to do 12,000 satellite. This also gives them leeway. Let's say for some years some recession happens and for a few years they don't make too much profit, they don't have to worry about maintaining 12,000 satellite. They will only maintain 4,000. And this launch that we are talking about happened on May 24th. So if my mathematics is correct, in July 24 you should see it, or June 24 you should see it. So this is the idea, first basically brick foundation of this real idea, because till that point it's just a dream. Now it's an actual thing. So if you have checked my Rocket Monday video about basically how do we launch multiple satellite from one rocket, the first thing you have to worry about is the weight and size. That's absolute. So weight wise, these are heavy satellite. Now they may, because they are looking so compact and tightly packed, we are not getting the understanding of the weight. Think of it this way, they are weighing as much as a motorbike. They are 230 kgs, less than that. Now you have to understand, they are the generation 1. They do not have inter-laser communication, basically inter-satellite laser communication. Without it, it's basically Gen 1. And they will have it, like they were planning. It's not that it's a recent idea. That was the foundation of it. The satellite network will not work without that laser network, and they have to have 4 of it, basically one to communicate back and front, like back front, one to back, one to left, one to right. So they need 4 basically receiver diode units. So it will add weight. How much, we don't know. In second generation we should find out. And the flat panel design is very thoroughly designed for one thing and one thing only, so we can pack as many as them. This is the luxury of having your own rocket company. They had the foundation understanding of the payload fairing. So payload fairing was the they went with, okay, this is the payload fairing, make your satellite fit into it. So this is why the design is so unorthodoxical. Now 60 can be fit into one. Now of course they may try to add more, squeeze more, because if they can, let's say, add even few millimeters from basically remove few millimeters per satellite, they can still add like 1 or 2 stacks of it. So there is still room to grow, but don't expect too much. Like 60 is like they're good with it. Now how do they deploy it? This is a tricky part. Rocket is in putting the main heavy inertia, and rocket is like, okay, now you are at orbital speed, but what do you do afterwards? So what did the rocket start to spin? How the heck is spinning? The engine is spent, however it still has what we call as cold gas thrusters. Using that, it spins. Now you might be like, wouldn't that throw satellite everywhere? Yes and no. It does throw them outside of the casing. Basically once the payload fairing is there, the structure will still retain there, but the satellite will start throwing out. Now why the reason it's not thrown out like everywhere in other orbits is simply because there is not enough energy. The spin they are doing, if you have seen the live footage, it's not like, it's very slow. It's just enough to let them out. And once you let them out, the majority of the inertia is still from the rocket. That's why the orbital velocity they have, so they can't fight the orbital velocity. So they will be out of the casing, nothing more than that, and then they will slowly fade away like a train. If you have seen the video footage of ground station, you can easily see it throws away as a satellite, and that's why it's visible from ground Earth. Because once it becomes This one once it's like thoroughly spread out, you won't be able to see it easily. You can still see it, but you won't be able to see it that easily as was shown in the video, because that point it was still clumped. So that's just throwing out, and that's not enough. Of course, you are talking about a satellite constraint, you need precision here. So all of the satellite itself will do self guidance. So this is the size and weight aspect of it. This is the luxury of having your own rocket company. Everything about this is like done back and forth. Basically how iPhone does, like, software and hardware communication, they have the same luxury here. Then we come to the, okay, now you have satellite. How do you power the satellite and you provide propulsion for it? Now powering part, this is, they are doing something interesting. Basically, if you have seen any satellite, if you just type satellite image, you will find a satellite that's like a person and it's like having two solar farms, I'm saying basically two solar panels on both sides. That's too expensive for them because they have to mass produce 12,000 of them. They are thinking in basically how we think about mobile phones in terms of manufacturing. So they are like, okay, let's throw one away and make one big one. One bigger is cheaper. Now on top of that, if you have paid attention to any satellite design, you must have noticed most satellites generally have either a black hue to their solar cell or a brown one. The reason for that is many times they use different kind of solar cells. Sometimes they use what we classify as multi-junction solar cells. Those are very efficient. Like these puppy can barely go to 20%, 20 plus, and those puppy can go upwards of 40 plus. So of course in the same surface area, same weight, you will get more. However, they are ludicrously expensive. Basically if this is 10, that is 1,000. So it's not that you're getting that much more energy. So they are like, okay, we have to think about money because they have to make 12,000 of those. So they are using cheap normal solar. Of course these are space graded, space rated. So it's not a like run of the mill source, but they are not like latest and greatest multi-junction 56% efficiency cell. They are normal cells. So that's how they are saving money, and they are making it into one array, and that array is simple. It folds out like a paper, nothing fancy about it. One array, one mechanism, done, saved money. Then what about the engine? Now this is the tricky part. They are using krypton based ion engine. You can check my video about ion engines here. Now many of you have seen early videos that they are using krypton because it's cheaper. Yes, that's true. However, there is another aspect of it. You have to think of it this way. Xenon engines have been like foundation of all ion engines. They work. NASA have been testing it for 10 years and using it for 10-12 years. So why the heck they are using this, basically krypton? Now they don't want satellite to last very long. The idea with these satellites is basically more like a use and throw. They are not making like this satellite, I'm going to make this satellite, put it there, and it's going to last for 10-20 years. They are not aiming for that. And using krypton saves them a lot of money. That's the primary motive. However, krypton is corrosive. When you ionize krypton, it becomes very destructive to the engine. Basically if you fire the engine for long enough, it's going to destroy itself. That is why NASA cannot use krypton to save money, because the price difference between krypton and xenon is ludicrously huge. It's again the same like solar cell and all that, but again NASA's mission is like, okay, let's say you are sending a mission that is like gonna take 10 years or 20 years. You can't have an engine that's gonna self-destruct. So that is why they have the luxury of using krypton. That's why it's not like people want to use expensive fuel. They have to use it, otherwise the engine will be destroyed. In this case, they don't have to worry about it. That's why cheap solar panel, cheap fuel, cheap engine. So that's how they are providing the power and propulsion. Then we come to the aspect, okay, now you have power propulsion, but all you have done is like send them into an orbit. Okay, you're not gonna be thrown out of the orbit, and let's say you fired the engine and you spread them apart. How the heck you gonna know where you have to place yourself? Because each orbital plane is supposed to have 60 satellites, so that means 60 has to be equally spaced out. How the heck you gonna maintain that? So for navigation also, they are not relying on ground based. They have their own board navigation system. Now of course they can't have the luxury of GPS, because GPS is not very good at high altitudes and polar region, and on top of that it's really not meant for guiding something that is as high as 500 kilometers from sea level. It's just not built for that. So they are relying on star trackers. Now star tracker is ancient technology. This is what we used to rely on, basically how to go to moon. This technology works, and this is like a fail-safe for ICBM. So let's say America launched ICBM, somebody took out the GPS system, the ICBM will fall back onto a star tracker system. And the reason why SpaceX has this technology is because their Dragon capsule also has this. This is kind of a requirement. Every Tom, Dick and Harry which has any experience in space, they know how to build this. So they have the luxury of in-house development. They already had this, they just put it there. This way they know where they are in the orbit. And on top of that, now they have an engine, they have a navigation system, they have a lot of power. They are relying what we call autonomous collision avoidance system. Basically, because there is so many satellites and they are aiming for 12,000 satellites, and not to mention a lot of debris, international space station, other garbage that will be there, and other CubeSats, because CubeSats are generally thrown in the same orbit as they are planning for, they must avoid quickly. Now, generally, satellites that right now have engines, that generally require a long process. Basically, there is a division in government known as Department of Defense. In that division, there is a department known as debris tracking system. They will make a phone call. It's like, hey, this satellite is about to collide to this satellite. There is a warning issued, and then there's a long chain about it. Now, that's okay if you have to only 600 to 700 satellite to manage, when you have 600 satellite that can do, maneuvers. But when you are talking about 12,000, that's not gonna cut it. And not to mention, they are very close and traveling very fast to each other. At the closest point where two orbits will intersect each other, they can come as close as 100 kilometers to each other. Now, of course, you have to understand 100 kilometers is a long distance, and you're talking about something that is the size of a motorbike. It's not like, a giant building coming to each other. It's very small things. So to make sure that they don't end up hitting each other, is basically they have their autonomous, basically computer on board using all the sensors will make the decision what should I do and how should I do it. And on top of that, because they are directly, basically the satellite itself is communicating to Department of Defense debris tracking system, so it can directly receive an alert. Basically, Department of Defense issues alert, like, this because when you are talking about debris, not every time you're gonna have the luxury, okay, this is one big debris that's traveling. Generally, you will have a cloud. Basically, this cloud has a lot of nut bolts and all that, and we are tracking this cloud. Okay, this cloud, avoid the orbit. Okay, the system will directly receive the signal from the system. No human will be involved, and it's gonna using the onboard engines and directly avoid it. And using the charter, it will realign itself. This is the navigation part. So these satellites are really next generation compared to all other satellites. This is on a whole different level. Then we come to the actual part. Okay, those are about satellite. How the heck is gonna give you internet? Now, per satellite, one satellite can go upwards of 20 gigabits per second. Now, that may sound a lot, and actually it's not that much, because if you divide it, like you can barely give 100 Mbps to 20,000 people maximum. That's not a lot, and that is the reason why they are aiming for having that many satellites. This is the reason they are targeting, to make sure that they can take care of everybody on Earth while giving them around 100 Mbps, and for some clients 1 gigabyte per second. Think of it this way, like if they are feeding data to, like, let's say 5-6 stock market, each stock market will be demanding 1 gigabyte per second, one satellite dedicatedly done for them. So this is not that much. That is why they are aiming for this kind of mesh network, and the mesh network will only work as long as they have optical inter-satellite links, and this is their proprietary part. This is the part they are keeping under wraps. This is the thing this is their golden goose. So the satellites have 4 antennas. If you check my Future Friday video, you understand what these antennas are. And basically they are phased array. And what I can guess, like, I'm not certain about this, but these 3, basically the 3 in the front, they are for communicating from the ground station, basically communicating from user. And the last one, basically the end one, this will communicate to the ground station in SpaceX. Basically SpaceX will have ground station where the data will be flown into, and that will communicate to wherever it has to go. Now, using this method, problem is you simply cannot give satellite internet, because every satellite has to communicate to the ground. That is why they have to develop that optical inter-satellite link. So that way, let's say you are in United States, or you are like, okay, I need to communicate to basically Shanghai. All you have to do is send signal to the satellite will take the signal. They have a different protocol, because normal internet protocol and DNS architecture simply will not work. They have their own protocol. It will find out where it has to go. Using that data, where it has to go, it will literally use laser to travel around, and that way, first, laser will travel much faster than optical photons in the basically optical fiber, because optical fiber is not vacuum. It does slow down in light. So you will have like your gateway to directly satellite through laser by laser. So 5-6 links down below, they will be like, okay, this is the ground station, and directly communicate. That way they can actually achieve lower latency than undersea fiber. That's the whole trick. That's why they want to do this. They can actually cut down, especially in long distance, not in short distance. Don't expect this to beat your land system, but at longer distance, this will beat any undersea cable, because you have to understand there is a lot of linkage before you even go to your undersea cable. Here you will directly be in space, like one ground station to basically satellite converts it into laser is traveling in actual vacuum. It will travel very fast and directly stay down. So that is what they are aiming for. Now, in terms of bandwidth, think about it. On early days, it will be exactly like your 5G mobile phone, because they are using same bandwidth like Ka band. And in terms of gigahertz, that's upwards of 25 gigahertz. This is Gen 1. Now, Gen 2, they will use V band. V band can go upwards of 75 gigahertz. Now, in terms of their optical connection, basically point-to-point connection, they will be aiming for 10,000 gigahertz, because it's an optical frequency. It's not a radio frequency, it's an optical frequency. Maybe generally lower infrared or higher infrared than that. So without that laser communication, this is just Gen 1. This is just prototype them, like, okay, let's send out satellite, but can we send it out? Can the ion engines can keep track? All that. I think that's what they are targeting for. So the second generation, until we have like, optical interlink, these are very low end. So once we have optical system, then the satellite internet would be actually beginning. This right now is just the foundation. Once we have the inter-satellite link, then we are like really this close to having actual, just go to a market, buy SpaceX internet, that would be around $100 to $500, and just put it on your roof, connect the basically optical fiber or whatever, Ethernet or 10 gigabyte per second Ethernet to your computer, and that's it, done. So we are very close, like we are really close at this point in time. In next 5 years, we should have at least one service provider providing us space internet, and every other competitor, they are flat out, like they haven't even launched anything that I can say, like in terms of one internet that they are actually doing it. They have to rely on Russia, basically Roscosmonauts, to get their satellite launched. That is the basically slow link in the chain. So even if they are mass producing the satellite, they can't send it outwards. SpaceX does not have that bottleneck. That's why SpaceX can pull this off. So this was my presentation on basically Starlink satellite. I hope you liked it, learn from it. In that case, please press the like button. If you didn't like it, don't worry about it. You can press dislike button. I would urge you to press it twice to show me your extra disappointment. And please leave a comment, because I reply to all of them. Just subscribe, press the bell icon if you're free. And as always, please check my other videos. I have also a lot of other videos. And as always, thanks for watching.